And then the rest of it I made up on the spot.
No, I think the choice is pretty easily made.
So, guess who's on top?
Praise the sun.
Praise the sun.
Praise the sun. Praise it.
And John and Alexandra and Claire, who stopped coming to class. We should all beat Claire. Claire's not here, is she? Yeah, Claire's bailing. Have to kill Claire.
I'm not even on the top
Spencer will be
anymore.
next.
It makes me sad.
Claire was never in all.
He used to put my
Okay, so we're going to get started. First of all, just a reminder, on the course website, there are links to the tutorials that Amanda Kastner has put up. So if you've been struggling with any of the material over the last couple of weeks, that's a good sort of really elementary resource. It covers index notation, it covers tensors, it talks about these representations, dual representations and all that stuff. So each video is maybe like 10, 11, 12 minutes long. It's got a little quizzes throughout to kind of help reinforce the ideas. So if you've been struggling with this stuff, that's a good resource. And again, it's kind of a steep curve at the beginning of this class because a lot of the ideas are new, a lot of the notation's new, but I promise you will get familiar with it. So just hang in there. So what we're going to talk about today are tensors. And I remember when I was in college at Georgia Tech many, many thousands of years ago, and I had this friend Jamie who was not a physics major, but he was at Georgia Tech studying something fancy. And I just remember the first time I ever heard the word tensor was out of his mouth, and he was talking about the Feynman lectures. And he was talking about how hard they were, and he goes, because he gets into tensors. And he raised his fingers and he did this, and I was like, tensors, like it's tensor, it's weird. So I've had this image of Jamie doing this in my head ever since then whenever I talk about tensors. But we're going to talk about tensors today, and I think you're going to find that they're not nearly as scary as my friend from way back in the day made them out to be. Okay, so I'm going to proceed, and this is the way I like to do things in this course and other courses, is just to really proceed by as close of an analogy as possible to things we've already talked about. Sort of just reiterating the same underlying schemes and points, because really we're just taking some ideas and just sort of building onto them, maybe going a little deeper in abstraction. Yeah, so without any further ado, I'm just going to write something. Because I could just stand and listen to myself talk all day long. It's so good. All right, so tensors, first and foremost, represent physical quantities, or they describe objects, if you will, physical quantities that are invariant but often, or typically, or whatever word you like, when expressed with coordinates, have components that transform. And this language should be very familiar to you, because this is, after all, the language that I used when I defined what, Jacob?
A vector.
And what else, Kellen?
Not one form but the other name, the dual vector.
Dual vector, good. Man, we're going to go through a lot of these today. I'm going to get a whole bunch of cards. I can't do those, everybody. Okay, yeah, we're going to go through everybody today. Sweet. Yeah, and in fact, it probably comes as no surprise to you that vectors and dual vectors are examples of tensors, and so the verbiage should be appropriate. Okay. Now, the place where things get a little bit new is when we ask, well, where do tensors live? Because we talked about vectors living in where, John? We might have more than one John. John Gill?
Oh, yeah.
John Gill. Where do vectors live?
They live in Minkowski space.
We do have vectors that live in Minkowski space, but if we're on a curved space, we have to think a little bit more sophisticated. We haven't gone to curved space yet, but in anticipation of that, we have stipulated that vectors live in the tangent space. Good. So in the tangent space to each point. What about dual vectors, Alexandra? Where do they live?
The cotangent.
in the cotangent space over each point. So vectors live in tangent space, dual vectors live in cotangent space. Where do you think a tensor lives?
Everywhere. Super tangent.
Super tangent space? No, dual vectors, so dual vectors live in generally tensor products, self-referential in its definition, in tensor products of tangent and cotangent spaces. That might sound a little bit weird, but you'll see what I mean by that in just a couple of minutes, all right? So really and truthfully, these are our two sort of key ingredients into the way that we're going to think about space-time tensors. I should always reiterate, because the notion of tensor can arise in many different contexts in mathematics, but we're focusing on space-time quantities in this class. So before we start digging into what some of these things mean, I'm actually just going to go ahead and give you a labeling scheme, because to talk about more general tensors, we kind of have to be able to distinguish between a vector, a dual vector, and other kinds of tensors. So we're going to have a scheme where a tensor is going to be labeled by two numbers, and the first number is going to be the number of tangent space factors in this tensor product. And then the second is going to be a number corresponding to the number of cotangent space factors in this product. Okay? And just to kind of drive this home and make this very, clear, let's go back to some examples that we've seen. So first of all, I can talk about a tensor which actually has no labels in tangent or cotangent space. That is, you can define this quantity without ever introducing tangent and cotangent spaces at points on a space. So what kind of tensor do you think this refers to?
Scalar.
It's a scalar, exactly. It has no components. Remember, we use the tangent spaces and the cotangent spaces to break things up into components. So sure enough, there we go. There's a scalar, probably the first tensor you ever encountered, and in this language we would call that a 0, 0 tensor. What do you think a 1, 0 tensor might be an example of?
It's a vector.
It's a vector because it has one index which labels one element or one tangent space. We only need one copy of tangent space, and that's exactly what a vector is. How about a 0, 1 tensor? It's a dual vector. So you guys are already experts at this. Okay. Just based on the kinds of things that we've seen, would anybody like to take a guess at, actually I've got cards, Spencer. Are you Facebooking?
What?
Are you Facebooking? Facebooking.
I am taking notes.
I'm kidding. Whenever I see my girlfriend on her computer or her phone, I'm like, are you Facebooking? She doesn't Facebook something. Are you Facebooking? She's not Facebooking. David!
Is that my question?
I totally forgot what I was trying to ask you. Yeah, you get a buy. You get a buy on that. Your question was, are you Facebooking? You weren't. Now, David, can you give me an example that we've seen so far in this class of a 0, 2 tensor?
Oh, 0, 2. Oh, right. No, I forget.
Okay, anybody want to take a guess?
This was actually going to be my question, like what is a 2, 0, or 0, 2? And I would guess that it would be something like, or 0, 4 would be something of 4 elements, like time-like component, and then like X, Y, Z, or like X and Y.
Well, no, so, okay, I got hands crossed American.
So let me come back. Like it's a tensor that needs two dual, or it has two covariant components.
Yeah, you love covariant, I hate covariant contravariant, but it's fine, it's fine. It is fine. So what tensor have we seen that has two contravariant components? Wait, two dual components?
Dual metric?
The metric, actually. So remember the metric in Minkowski space we wrote as eta mu nu. So just to remind you, when we actually write these things, and we're specifying their components, we say things like this. So we write vector components with an upper index, dual vector components with a lower index, and so if we're talking about a 0, 2 tensor, we're talking about an object with two dual vector indices. I'm not talking about what values the index take. The values are always the dimension of space-time. So this mu goes from 0 to 3, because we live in a 3 plus 1 dimensional space, time. And this nu goes from 0 to 3. Okay? Who would like to take a guess at a 2, 0?
Is it a dual metric?
It is, well, so the metric is a very special case. Yes, we would call it the dual metric, but this is actually the inverse metric, which we write as eta with 2 upper indices down. That's a special relationship, so I should be, and we'll come back to that at the end when we talk a little bit more. Okay. So we've already seen, actually, and kind of worked with a little bit examples of higher rank tensors. But you can now imagine that, you just go home and you can make up the most scary tensor imaginable. You can write some t, mu, nu, alpha, lambda, beta, gamma, delta. Will, where's Will? Will, what kind of tensor is that?
The horrible one.
But in terms of this naming scheme.
Oh, it's like a 3-4.
See how easy this is? It's like counting. God, it doesn't get any easier than that. Okay, so that's our labeling scheme, all right? And it's going to be very, very important to note whether the indices in question are indicating elements of tangent space or indicating elements of cotangent space. Okay, so now I am, well, first of all, let me remind you of something I said at the end of the last lecture, which I've already kind of taken advantage of. And that is, tensors are generally, if you express them fully, they would look something like this. So these are, okay, so, get ahead of myself. What does that right there indicate? Is that a tensor? No, what is it? It's the components of a tensor. Okay? In the same way that those are the components of the vector, those are the components of the dual vector. If you would like to see what this tensor looks like, it looks something like the following. The tensor T that corresponds to those components is T, mu, nu, alpha, lambda, beta, gamma, delta, omega mu, omega nu, omega alpha, these are hats, and these, oh my God, I'm doing an awful job here. Oh my God, I'm doing a terrible job. I'm not even getting it right. Don't copy that down, I'm a crazy man. Jeez. And omega, like, he's gonna write them all up there. He's really gonna waste our time. And I think I'm gonna do it because I just want you to appreciate one thing, which I'll say at the end when I'm done, if I ever get done. I don't think I'm ever gonna get done. Why did I pick a tensor with 7 indices? Okay, that is what this tensor looks like. Remember, it is a linear combination, these are the coefficients of the linear combination, of a bunch of vectors and dual vectors in the tensor product space.
That's the circle with the X.
Yeah, it's the circle with the X. Okay? We are going to be able to do everything we do in this class with those. Doesn't that make you happy?
That we don't have to write out those?
Exactly. And I'll come back to this if we get to this point at the end of this lecture. This is a very important part of the tensor story. But fortunately, we know that as long as we're consistent and everything works out for the components, and the transformations work out right for the components, the transformations for all of these basis vectors and basis dual vectors will compensate for the transformations here, making this whole thing invariant. That was the thing we talked about last time, where we said that a vector v mu has a linear combination of a bunch of basis vectors is an invariant because this transforms one way and these transform in the opposite way, and they offset each other. Same thing's going to happen here. Each of these is going to transform if we do a coordinate transformation, And each index here will also get a transformation which offsets it. So it's going to be a consistent story as long as we're careful in our components, and you'll see what I mean by that in due time. And so yeah, it's nice to abbreviate things. Okay, so now I'm in a good position to define a tensor. And I know what you're thinking. Ariel, what are you thinking?
I thought you said you knew that.
I want to make sure Ariel knows what he's thinking. No, what you should be thinking is, didn't you just do that? Didn't you just define a tensor? Okay, no, now I want to give you a tensor, and I'm going to give you two definitions of a tensor. And the first one is a popular definition, and this is the definition that you actually hear from a lot of people when they're trying to explain what tensors are. And I love it. It's one of the greatest definitions in all of physics and math. A tensor is a very special thing. It's a smile, a tear, it's a soft summer rain. It has no beginning. It has no end, but I like tensors best when they're shared with a friend. A tensor is something that transforms like a tensor.
What's the point of the definition?
Huh?
What's the point? I mean,
You're bothered by that, aren't you?
it's like a cup is something that looks like a cup.
You need some fuzzy bunnies on a soft summer day. Okay, I'll come back to it. Let me give you another definition that might make Martin happy. Okay, Martin, here's yours.
It's
So,
worse than the first one.
tensors are multilinear maps. From the space of vectors and dual vectors into the reals. And again, these are space-time tensors, so all the coefficients we're dealing with are real value. Okay? Does that make you happy, Martin?
I mean, it's a definition that's not circular, so sure.
Okay, all right, so I'll flesh this definition out in a minute. But what's interesting is we will actually use this definition more. For the following reason, and this is going to be a crux in general relativity. We're going to write things down, and then we're going to be posed with the question of, is that quantity a tensor? And the answer to that question we will find by simply asking, how does that quantity transform? If it transforms like a tensor, then we will say, yes, it is in fact a tensor. And I know you might say, well, how are you going to figure out how it transforms? Don't you just have to know how? You'll see through example. And that will actually be a very, very important segue into the formal math of general relativity, but more on that in time. To kind of see what's going on here, and by the way, if you want to write that, you can say T maps dual vectors, dual vectors, dual vectors, dual vectors, 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 vectors into a number. Okay, to kind of see that second definition and what it means, we can consider a well-fed tensor. Because we talked about this last time. Everybody likes to eat. So if I take my tensor T, oh my God, I really picked a winner with this tensor. Lambda, beta, gamma, delta. Okay. If I took that tensor and I fed it a bunch of vectors and dual vectors. Now everything I'm going to do now is for the components of everything. I'm not going to talk about the basis vectors and the basis dual vectors. I'm literally going to feed it a vector, which means I'm going to feed it something like this. But I'm only going to write the components, okay? So if I feed this thing vectors and dual vectors, if I feed it, and and how do I write, yeah, write it like that. So if I feed it a dual vector with components v lambda, a vector with components v lambda, another vector with components v beta, another vector with components v gamma, v delta, and then a dual vector with components omega nu, and omega alpha, okay? I am now combining 1, 2, 3, 4, 5, 6, 7, 8 objects. This is not this thing with a bunch of basis stuff. This is literally 8 different objects. But the combination of all 8 of those objects is a number. Because think about it, there are no indices that are not summed. Every single index is summed. Yes?
Is here vectors and dual vectors switched? Because I thought vectors were the top indice.
Yeah, so this is a vector, and this is a dual vector.
Yeah, but you wrote the vectors from the bottom indice of your tensor. Lambda, beta, gamma, delta are on the bottom.
Right. So the language that I should say is, this vector eats this dual vector index.
Okay.
Because remember when we talked about combining vectors and dual vectors, the whole point was that if we combine a dual vector with a vector, that gives us a number, or an invariant. So yeah, that's what I'm doing is I'm pairing up dual vector indices with the requisite number of vectors, okay? So this thing is just going to be something on the reals. It's going to be a number. And as a number, it's going to be invariant. Okay? Now, we can be mean. We can starve our tensor. And we can just say, well, I'll give you 2 vectors and a dual vector. Okay, that is an underfed tensor. He's starving. What kind of object does this result in? Nathan.
Let's see. Yeah, I'm going to eat those 2, and it's going to redo one of those. It's going to redo I got 2 indices on top.
Yeah, it'll be a 2-2 tensor, and just we might as well call it something. I'll call it M nu alpha gamma delta. Okay. You might notice that I will start getting a little sloppy with moving indices or worrying about like these indices being left or right or whatever. And part of that is because we're just going to forego ever trying to make something like this into a matrix. So we don't really need to know which one's on the left. There will be some importance to the ordering of things, which we'll see in due time, but occasionally I might get sloppy and write that, and you might worry that these are directly under those. Well, you'll never write that as a matrix, so it wouldn't matter. Okay? We can also overfeed the tensor. We could put in more vectors or dual vectors than this thing is actually willing to eat, and in the end, there will be some leftover vectors or dual vectors to spare. So, and that would leave us with a different tensor. Okay, now, yeah.
Does it matter the order that you multiply in the vectors and dual vectors?
You tell me.
Cool.
Did that change the answer?
I don't think so.
Why not?
Well, I would figure that they're that essentially they commute, but I guess that's not really the
Well, an index notation. Well, if I'm feeding it the same vector, an index. It's actually that's a really good question. So I've been a little bit degenerate here because I'm calling all these the same V. I don't actually have to feed this thing 4 copies of the same vector. I could call that a V1, a V2, a V3, and a V4. Then the order matters because this V is going with this dual index. This, which is a different vector, is going with this one. And if I switch them, I'm pairing up different vectors with these different indices. Then it would matter. But if they're all the same vector, then the order doesn't matter with respect to the indices because I'm going to do this Einstein summation convention to combine them, and we know the order doesn't matter. So yeah, that's actually a really good point. Go for it.
If we sum over the same indices with the same, they all have the same space, so they're all like the 1 plus 3 dimensions or whatever. Why then does it matter? Because aren't we summing them over the same numbers and same components?
So, yeah, okay, so imagine I have a tensor t mu nu, and just in 2 dimensions to keep it simple. I'll just say t11, t12, t21, t22, and then I combine that with a vector v mu and another vector w mu. Okay. At this point, if I use the summation convention, I'm going to be pairing. In summing this, among other terms, I will have T12, V1, W2. Okay? But I will never have this particular component paired with this combination with the order switched. I will have T21 with V2, W1. But there's no guarantee that these 2 components of that tensor are the same. In general, they won't be.
And then there's not just like an obvious commutator, it's just like, it's a very different operation. Okay.
Okay, so that's kind of our second definition. We can just think of tensors as maps. And when we say map, what we mean is we take a bunch of stuff and we do an operation on it. In this case, it's combining this set of stuff with the tensor, and it maps all of that junk into a number. Okay? Now let's go back to this definition. And again, this is the one we're going to use most often. And this is where everything that we did last time is going to pay off big time. Okay? How a tensor should transform is entirely indicated by its index structure. So what do I mean by that? Well, let's take an example of a scalar, which I'll just call C. C, if I transform the coordinates that I'm using to describe this scalar, becomes C prime. And how do I get C prime through an operation on the original C? What do I do? Yeah, I don't do anything. It doesn't transform. It's invariant in itself, even when expressed in a coordinate system. In terms of index structure, C has no indices. The scalar doesn't have any indices. There's nothing to transform. So the transformation is trivial. The scalar has the same value even if you use a different coordinate system to express things. Of course, we already know that if I have a vector or a 1-0 tensor, which we should now call it, if I transform coordinates, I can get the new components from the old components by the application of the lambda, where again, these are the isometries of Minkowski space. This isn't a general coordinate transformation. These are the boosts and the rotations. Dual vectors. Okay. What would I use to get the components of the dual vector? Parker, there he is.
You'd use a similar transformation, except you'd switch the indices.
Yeah, and how is that related to this transformation up here?
It's the inverse.
Yeah, it's the inverse, exactly. Okay. Now we've seen all of these. Now comes something new. If I have T mu nu, a 2-0 tensor, and I transform coordinates, all of these indices get transformed. Remember, for tensors, we're always going to have everything either primed or everything unprimed. But to transform each of these indices is just like transforming two vectors. So we literally just write a transformation for the new index and then a separate transformation for the new index. Now, let me go ahead and say something that you should be very, very careful about. And I know this is played out in one of the examples in Amanda's tutorial, and you'll probably see it in the homework. I might even talk about it in a minute. You know that these lambdas can be represented by matrices. Please don't look at this expression and say, oh, I just take the rotation, say if I'm doing a rotation, I just take the rotation matrix, square it, and multiply it by this matrix. That's not what you do. First of all, you know that if you want to convert this to a matrix expression, that we have to get the indices that we're summing over adjacent. So the first thing I have to do is write this as lambda nu prime mu, then t mu nu, and then lambda nu prime nu. And if I call lambda mu prime mu the original transformation lambda, we know that this is the inverse transformation. And then if I want to switch the application of the indices, I should be thinking of the transpose. And I'm going to write this, although I don't like this expression, but I'll write it anyway. If I were ever tempted to write something like that, then that would be lambda transpose. But I'm just saying that because if in your mind you want to say, oh, I have to switch the nu and the nu prime so that the nu here is right next to the nu there, the thing you should be doing is saying, I should be writing down the transpose of this matrix. Do not switch the indices. Okay? And then last but not least, we can have the transpose of the inverse. I'm out of room. And you know what that looks like. So if I wrote lambda mu prime, that would be lambda inverse transpose. Okay? So in terms of matrices, we can evaluate the transformation of this with a lambda t lambda transpose. Okay. Again, this is a matrix expression. Yes?
So in the vector versus dual vector lambdas, it looks like you've switched the application, but we're calling it inverse there, but transpose over here when you switch the application of those?
No.
Or-
So when I switch prime with unprimed, that's just going to the inverse transformation.
Okay.
The transformation takes me from the unprimed to the primed coordinates. And so actually you can think of it as the transformation takes you from the lower coordinates to the upper coordinates. So if my original transformation is taking me from unprimed to prime, the inverse would take me back to the unprimed.
Oh.
That's the way you should think about this.
And then the transpose, the way you wrote it, you like.
I really hate that I wrote this, so let's just ignore that Alex wrote that. And let's just remember that when we want to go from an expression like this to a matrix, God, what is so hard about saying matrix expression? As a matrix, you need to have this thing organized so that this index is adjacent to this, so transpose the matrix.
Okay.
Okay. So a couple more examples. We can look at how a mixed tensor would transform. Here's a fun guy, h mu lower nu. Again, every index gets transformed. And I told you earlier on that I would write a lot of expressions like this because these transformation properties are what it's all about. So if I wanted to get the components of this mixed tensor from the components of the tensor in the original coordinates, again, I just treat each index as it is. Is it a vector index or a dual vector index? So I have a vector index mu, so that gets transformed with the normal transformation rule for a vector index. And then I have a dual vector index nu, so I use the transformation for a dual vector index to transform that guy. And you notice, like, if you're wondering how does he know what he's writing, I'm literally saying this side has a mu prime and a nu prime. So overall, this side better have a upper mu prime and a lower nu prime. There it is, upper mu prime, lower nu prime, and then the rest of the stuff just gets taken care of through the summation. That's literally how I'm deciding what to write. It's not that I'm going, oh, this is an inverse cotangent hyperbolic. Anyway, whatever. Okay, this is a fun one. How does a 0-2 tensor transform? If you want to write that as a matrix expression, you would actually write that G prime is lambda inverse transpose G lambda inverse. So painful. Okay. So I'm just giving you just sort of some prototype examples. You could write down the transformation law for an arbitrary tensor. You could transform that T that I wrote earlier. You too can transform that tensor. All you do is throw enough lambdas on there to take care of all of these indices. Okay? And then if you wanted, well, you couldn't. So could you turn the transformation of this into a matrix?
Matrix.
I've talked too fast. You try. Say it.
Matrix expression. Matrix expression.
Say it. Do it. Matrix expression.
Matrix expression.
It's hard, isn't it?
Matrix expression.
You guys back off. Fired. I'm in a new class. Okay, yeah. But you could not convert the transformation of this to a matrix expression because you can't express this as a matrix. This is kind of it. Like second-rank tensors, we can indicate as matrices. Rank 1 tensors, we can indicate as column and row vectors, or column and row matrices is what I should say. And then this is, of course, a number. But as soon as you get 3 or more indices, you can't write it as a matrix. But now we see the egregious error in claiming that a tensor is really just a matrix. Because after all, if I gave you 4 elements and said, is this a tensor in a 2-dimensional space, just to make it easy, you would not know which of these types of tensors it would correspond to. Just giving you an array of elements doesn't tell you how that thing transforms. I would have to tell you, is it a 2-0 tensor, a 1-1 tensor, or a 0-2 tensor? That's telling you that it's a tensor and what kind of tensor it is. But all of these 3 objects, they're very different objects, transform in very different ways. All 3 of them could be expressed at the end of the day as a matrix. But just seeing the matrix is not going to tell you everything. This is why you have to just not accept that a tensor is just a matrix. A matrix is a convenient way to display the components of a tensor, but you have to know what the hell the tensor is that's called in the first place. Tensors are all in their transformation properties. That's where the love is. Okay, so now that we've got a couple of definitions down, we've looked at some notation, let's actually talk about some special tensors, because there are some tensors out there that are a bit special. So first of all, the metric tensor, and for now we're still doing special relativity, so our metric will still be eta. The metric tensor is it is the canonical way to take a vector and turn it into its corresponding dual vector. So what I mean by that is the metric eta mu nu it lowers indices. So if I have a vector v mu, and I want to turn it into its corresponding dual vector v nu, I do that by applying the metric to the original vector that I started with. Now, I want you to notice something very important, and this is a distinction that is important to be made. I can write an expression like this, m mu nu v nu. I can combine a 0-2 tensor with a vector. And if you look at the indices, that dual vector index nu and that vector index nu are combined. This is called contracted. And so this object, at the end of the day, Annie, would be what kind of object?
I don't know.
Well, how many indices would it have free that aren't summed over?
One
And would it be upper or lower?
would be upper or lower.
So what do we call an object with one lower index?
Dual vector.
Yeah, it's a dual vector. So you might, here's the key, you might be tempted to call this v mu. Don't. Give it a new name. Call it h. Because again, it is only when we are lowering the index with the metric that we are taking a vector into its corresponding element in the dual space. All right? This will take you to an element of the dual space, but we have a sort of preferred mapping with the metric. And so we want to distinguish other kinds of mappings that we might do with other tensors. Okay? So I just want you to be aware, you can lower indices just by throwing on a tensor, but the metric is the only one where when you lower the index, you're going to get back the corresponding element of the dual space.
That's lowering it, but also not keeping it. You're changing mu to nu.
The name of an index is unimportant. Like, yeah, I know. So v mu and v nu, those are the same objects. And you know, I mean, on occasion, if I have to square something, I'll have to give its indices different labels. So, yeah, that kind of thing bothered me for a long time when I was
Okay,
learning
but
this
like,
too, so.
if you have eta mu and nu describe two unique things that I don't know what they are, but you're canceling out the nu part of it.
So this is literally labeling the different components of the basis in the dual in the cotangent space, or the in the components in the. Oh God.
Bases and
So the metric tensor would be expressed completely like that. So these are simply labeling the different basis dual vectors that I'm combining with this tensor product, and then forming a linear combination of those with these as the coefficients.
so taking the vector v with mu gets rid of the mu basis, but the mu basis is in a different direction than the nu basis.
No. That's so the nu and the mu, they are literally, it's well, I mean, yeah. When you say they're labels, therefore they're the same thing. That's a hard concept to kind of wrap your head around. But if I have 3 dimensions and I call this the x1 direction and the x2 direction and the x3 direction, and I refer to xi where I is 1, 2, or 3. And then I refer to xj, where j as well is 1, 2, or 3. All I'm saying is when I refer to this, I'm talking about something that can have components in each direction. And when I refer to this, it's the same object. It's an object with 3 components.
So it's not like a space perpendicular to x1,
No.
x2, x3 or something.
Yeah, no. This is labeling all of the components because mu takes values 0, 1, 2, and 3, and nu takes the exact same set of values. Okay. All right. Yeah. What did I say? Okay. Yeah. So and then the inverse metric. eta mu nu raises indices. So if I have a vector with some lower index mu and I want to get that to a vector with upper index mu, I apply the inverse metric. Or sorry, v. Now, these are not coordinate transformations. They are not, I'm not doing coordinate transformations when I use the metric to raise and lower indices. Every index is either primed or unprimed in these expressions. Coordinate transformations are done with the lambdas. Remember, these are the only objects you should ever be writing down which have one unprimed and one primed index. And they're always going to have a pair because they're going from the old coordinate system to the new. The old coordinate system to the new. These are transformations. This is not a transformation. This is simply taking a vector and returning the corresponding dual vector. Everything happens in the same coordinate system.
And when you transform, you have to transform over all indices at the same time, because it doesn't mean anything to transform, say, mu, but not
No,
mu.
it doesn't. It makes no sense. So that's what I was saying.
Yeah.
Here, you have to have a lambda matrix for every single, or a lambda transformation for every single index on your tensor. Yes?
Doesn't that mean you're bringing it from the cotangent space to the tangent space and vice versa?
Right, but everything is, so the cotangent space and the tangent space, we're going to build those actually explicitly, but those are all built with respect to a particular coordinate system. And so with one coordinate system and the basis in tangent and the basis in cotangent space for that coordinate system, I can move elements from the tangent to the cotangent. That's different than changing my coordinate system, which changes the cotangent and the tangent basis. So if I keep something in tangent space and change coordinates, that thing transforms, its components transform. Yeah?
So just to clarify, the transformations are not 1-1 tensors? They're not tensors at all?
Yeah, these are not tensors. So remember, tensors are physical objects. So my example last time, Spencer is a physical object. He is a tensor. If I flip him over, flipping him over is not a physical object, it's a transformation. That is a lambda. Transformation should be invertible. I can flip them over, but tensors are not necessarily invertible. I don't even know what that means to have the anti-Spencer, or the reverse Spencer, or the, yeah, I don't know. Okay, so, and look, this is the hard part of, I think, of this index notation is, everything's just a letter with a bunch of indices. So how do I know what's what? Well, I mean, the rule of thumb is to remember, a transformation is the only thing with one primed and one unprimed, and it should be that way because it moves us from one coordinate system to another. If you see an object that's got a bunch of indices, and they're all primed or they're all unprimed, that thing hopefully is a tensor. We'd have to check, but hopefully it's a tensor. It's a physical object. Now, so carrying on with these specific important tensors, the metric provides this map. Also, the components of this, well, we call it the inverse metric, but it's literally, if I call the metric, if I write it as a matrix eta, the components of this are exactly the components of the inverse matrix.
Yeah.
Let me point out to you why that's unique. I could take this tensor and express it as a matrix. Okay? However, I could then take each of these indices and raise them, creating that guy. This would not correspond to the inverse matrix. And you don't have to take my word for it. You can take this thing and raise the two indices by using two factors of the metric, find the components of this thing, and you'll see they are not the components of the inverse matrix. It is only for the metric that this special property holds. The metric is special in many, many ways.
Could you also say it's special because the matrix, I mean, the matrix form of it is its own inverse, like, period, right? Or no?
No, it's not. It's that case for it's that case for Minkowski space, yes.
Right.
But in general, no.
Yeah.
Yeah,
No,
in
it's
general
awesome.
spaces or in general coordinates. I mean, I should say even in flat space like Euclidean space, if you use spherical polar coordinates, the metric and its inverse will not be the same. Okay, so there's, I'm saying all this now, I'm trying to emphasize the parts that are going to confuse you, but when you work problems and when you do homework and we do stuff, this is going to come up. So just remember, oh, Alex said that there was all this really complicated stuff I need to remember. And then go back to this lecture or these notes and look at this stuff. So, all right, one more thing before we go ahead. Yeah, I'll do this. Because I love the metric so much. It's such a great thing. And the metric will be a primary focus in this class, even when we move to curved spaces. Let's do eta on eta action. Because I love some eta on eta action. Okay, so suppose I took the metric, eta mu nu, and I actually used the inverse metric to raise the two indices of the metric. So I'm after that. So to get that, I can apply one factor of the inverse metric to raise mu to alpha, and I can use another factor to raise nu to beta. Okay? I know, it's crazy, isn't it? Is everybody on board with that expression? I'm just making sure all my indices work. And remember, if I just want to take the metric and raise its two indices, I use the inverse metric to do that. That's what I use. Okay? But now remember that if we have the metric and its inverse, because these are inverses of each other, this is really just delta alpha nu. Okay. Of course, if I contract the nu with the nu and the Kronecker delta just says make the nu into an alpha. Notice the Kronecker delta here does not raise or lower anything. It simply says sum over the nu, but sum over it, and in doing so, simply replace this index by this index here. So this is just going to give me eta, beta, alpha, which, by the wonderful symmetry of the metric, or the inverse metric and the metric, is exactly what we're after. So another question we might ask is, what is this guy? Say it again?
Is it the identity?
The identity? What do you mean by the identity?
Kronecker delta with the same two indices.
Yeah.
Which is?
It's the trace of the Kronecker delta.
It's the what?
Trace of the Kronecker delta.
It is the trace of the Kronecker delta. Okay, so if we pretended for a moment that this was an alpha, then we would write delta alpha nu. But now let's go back and remind ourselves that that's a mu. Or sorry, this is a nu. Yeah, now let's go back and remind ourselves that that was actually a mu. That's the Kronecker delta, but remember, this is summed over. So this is literally delta 0, 0 plus delta 1, 1 plus delta 2, 2 plus delta 3, 3, which is, it's 4. A strange fact of Minkowski space is that the trace of the metric is 4, not 2. Right, if you just think of the trace of a matrix as the sum of the diagonals, you would have said 2, right? Minus 1, 1, 1, 1 adds up to 2. But this is our trace operation. All right, I got one more for you, and then we're going to move on to some other stuff. Questions? So we might ask ourselves, we kind of started our whole vector story by talking about how coordinates transform. And then we use the transformation of coordinates to tell us how the components of vectors transform. But there's another very, very important quantity in math and physics that we need to know how it transforms. And that is a quantity that is crucial if you want to talk about things that vary. In physics is interesting when things change, right? Physics is boring when everything is constant. You agree? You're learning. That's interesting. If you left the room as, yeah, anyway, things are more interesting when they change. But if we want to sort of quantify, mathematicize change, what do we tend to use to measure change? We use derivatives. So we need to ask ourselves, how does this thing transform? Okay? To get the transformation of a derivative, and we're going to talk about partial derivatives. I mean, everything can be built up out of partial derivatives at the end of the day. To figure out how this transforms, we get to use all that magic that we did last time. Okay? To figure out how this transforms, let's just ask how it acts on x nu. So what is d by dx mu of x nu? Say it.
Kronecker delta.
It's the Kronecker delta. It's 1 if this is actually the same. I mean, look, if that makes you worried, like let's say that I was taking the derivative with respect to x of y. It's 0. This is a partial derivative. If this happened to be x, you'd say it's 1. If this was ct and that was x, you'd say 0. But if this was ct, you'd say 1. So this is the Kronecker delta. But the Kronecker delta is a number. It's an invariant. Yeah?
You flipped them. You wrote the bottom one first. Is that significant?
Nah.
Okay. We've been writing the top ones first.
If you wanted to write this as a matrix, well, I like to write the bottom one first just because this operator is sitting to the left. But if you wrote the Kronecker delta, if you arranged it as a matrix, it would be the identity. So swapping the rows and columns isn't going to matter anyway. So we don't have to be too careful with the Kronecker delta. We don't have to be careful with the metric either, because the metric is always going to be symmetric. There will be tensors like the F mu nu of electromagnetism, which we'll talk about in a bit. The order of these indices actually matters because swapping them gives you a minus sign.
Okay.
So, but for a symmetric tensor, which could be represented by a symmetric matrix, we don't have to worry too much which one we put to the left and which one we put to the right. Yeah?
Also, whenever in a book, whenever I see the Kronecker delta, it is usually right above each other. Like one's right above the other.
Yeah, it's because they really don't, it doesn't pay to distinguish.
Okay, but that's true, then why go for the hassle of making vertical in the first place then? Because they make everything else, it's the proper notation just for the Kronecker that it's different.
Well, the left and rightness of things is really only important if you're trying to beat it into a matrix, which we're not going to do for the most part anymore. So it's going to become sort of irrelevant after a while. We will talk about some tensors, like we're going to look at this tensor. It's going to play a slightly important role in this course. I'm kidding, it's the most important tensor in this entire course. But anyway, we do have a little gap here because we do consider taking this tensor and lowering this, so dropping this into this spot. And if you put all these three underneath it, you'd have to scoot them over and make room for it and all that kind of stuff. So yeah, so we do kind of like to preserve some spacing so that we can raise and lower things. But the Kronecker delta is just so trivial that we don't ever do anything with it. Yeah.
What's the significance of the Kronecker delta having a mu in the denominator? Like, how did that happen? Because it's x.
It's an interesting question, and I'm about to come to that. Okay. But let's go back to that rationale that we played through like 3 or 4 times last time. Okay. If this is invariant, and we know how this transforms, how does this have to transform?
By the inverse of that operation.
By the inverse of that operation. So d by dx mu should become d by dx mu prime, which I get from d by dx mu by the application of mu prime. But what kind of object is that transforming like?
A dual vector.
It's transforming like a dual vector. In fact, in this class, we will often refer to this as d mu. To remind ourselves that the derivative transforms like it has a dual vector index. So the answer to your question is, the index is low because the index is high in the bottom. And there are people who will consider this thing, and they'll call that d mu. I think they're cray-cray, but some of them do it. You don't do it.
Why would that not be significant?
Because I don't know what this is. These are coordinates. I mean,
Oh, okay.
So the starting point of all of this was I coordinatized the space, and the coordinates I'm defining with an upper index, and then they're intimately associated with vector components, and yada, 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 yada. I really don't know what to do with that object. You could say, oh, you just get it from a coordinate by applying the metric, but anyway, they're the dual coordinates, I guess. So we're not going to write it that way. Okay, so here's our definition of our derivative, and it transforms like a dual vector. Okay, so moving right along. Other questions? All right, so a very, very important thing to achieve in this class is to make sure that we are writing our physics in terms of tensor equations. Okay. So what do I mean by that? Remember, the tensors that we're talking about, these physical objects that exist out there, they're doing things. You know, your car's going down the street, the tree's standing in the way, people's bodies fly. That stuff happens whether you've got coordinates or not. You can pick one set of coordinates and describe it. You can pick a different set and describe it. Okay? So how do we sort of embed that coordinate independence into our physics, bearing in mind that when we write down physics, we tend to write everything using a coordinate system. Okay? And the idea is we just make sure that the expressions we write down take the form of tensor equations. So for example, the simplest tensor equation could just be the equivalence of 2 scalars, because that equation is not going to change no matter what coordinate system I choose to use. Okay? But if this was the only physics expressions we could ever write was scalars equals to scalars, physics would be pretty limited. But instead we like to look at more complicated things. So we might like to say, you know, I've got, we might like to express Newton's second law, which relates vectors to vectors. And so we might want to somehow say that F mu is M A mu. Okay? But this is not itself invariant, right? Because if I want to transform this expression into a new coordinate system, both of these, each side would transform. Okay, this would become F mu prime, this would become M A mu prime, and this would look like lambda mu prime mu, F mu, and this would be M times lambda mu prime mu A mu, So I haven't exactly got back what I started with because I've got these lambda matrices. Okay, but that's okay because the components of things should transform. However, remember, this is only half the story. Because secretly, this equation is, these are vectors. This is F mu E hat mu equals M A mu E hat mu. Now when I transform this side, I transform the components of this, but then I transform the basis vectors, and everything cancels, and the expression all together is exactly the same. Okay? Now here's the thing. The basis vectors and the basis dual vectors, the omegas and the e's, the things we're never going to write, they're always going to transform the right way. The question that we're going to be faced is, if I have some object like this, is it transforming the right way? We know how this should transform if it's a tensor. And if it does transform correctly, then the combination of this with all of the, two dual vectors and a vector, or a basis vector and two basis dual vectors, that whole combination will be invariant. But if I find out that this doesn't transform the right way, like what if the transformation of this thing looked like this? T mu prime alpha prime equals lambda mu prime what if it transformed like that?
Gauge freedom? No.
That doesn't even make sense. Hold on.
Isn't that kind of primes?
Well, let's just add primes. Let's just put some prime indices on there. Okay, but the point is, if I took this and I combined it with the set of basis vectors and dual vectors to make it, E hat mu tensored with E hat nu tensored with omega alpha, okay? When I transform these three things, they're going to undergo their usual transformation rules. But then if this guy transforms with this funky thing, they're not going to cancel. Okay? Now you may say, well, why would you ever write something down that transforms like that? You're stupid. But we will write down things that don't transform correctly. Okay? In fact, we will discover when we go to curved spaces that the derivative doesn't transform correctly. And fixing that is where all the love's going to come in. Okay? So the point, the thrust of this is we want to make sure that the equations we write are written in terms of true tensors. Because then we're describing things in a manifestly coordinate independent way, which is the way the world should be. The world shouldn't depend on some special coordinate system that doesn't actually exist out there. All right, so I'm just going to finish up with a rundown of something that many of you have probably seen before. But we've developed all this machinery, so why shouldn't we say something about a place where you might have seen this before? So to get some appreciation for where tensors make things nice, let's consider these expressions. Anybody seen these before? I might have a different notation than you're familiar with. Tensor is just a matrix. Okay, so Maxwell's equations. How many equations does this correspond to?
What?
How many scalar equations does this correspond to?
Three.
Three, right. It's a vector equation, so it has 3 parts. So that's 3 equations. How about this one?
1, 3, 1.
Yeah, so we got 3, 1, 3, 1. We got a total of 8 equations. Okay? And now what I want to point out to you is, first of all, it might be obvious that these equations are invariant under rotations. Because after all, they are written in terms of true tensors under the rotation group. A vector with 3 components is a tensor under 3-dimensional rotations. Of course, these are scalar equations, so we know that they're invariant. Okay? But is it obvious that these equations are invariant under boosts? No. Why? Because we've written them in terms of 3-dimensional vectors. A boost is a manifestly 4-dimensional thing. It mixes time and space. So if we want to see that Maxwell's equations are invariant under boosts, in addition to rotations, we really need to write them in terms of 4-dimensional tensors. But we can do that. Go ahead and ask your question.
Is there a reason you didn't write epsilon naughts and mu naughts and stuff?
Yeah, because I'm not going to do that. So first of all, let's take the J here and the rho here. 3 things, 1 thing. Let's make it a 4 thing. So let's call the 4 vector current rho J1, J2, J3. Okay, so now we've got a current that's living in 4 dimensions. Of course, there's a question of, is this actually a vector? And it turns out this is a vector in 4 dimensions. But then the question is what do we do with all these E's and B's? Because, if we take E, which has got E1, E2, E3, and we try and add something here to make a 4-component E vector, what you going to add? Or what are you going to do with B? You got 3 components of B, and you need to add something to it to make a 4-component B vector. What you going to add? What you going to do? So we got to make a 4-dimensional tensor out of all the stuff in here. I just did it with J and rho. How am I going to do it with B and E?
Put them together.
In what?
Electromagnetic tensors.
Into a rank 2 tensor. So we have the rank 2 or the 0,2 tensor F mu nu. And this is, as many of you are aware, and I never know where to put my components or minus signs. There we go. Okay, so sometimes the generalization to 4 dimensions is not just add a 4th thing. Sometimes you actually have to be a little bit more sophisticated. But you've heard this before. You know that it's in relativity that you see that the electric and magnetic fields are really 2 sides of the same object. There is no separate electric and separate magnetic field. And it's really obvious here. This is the one object in 4 dimensions. It's a 0,2 tensor. Some of its components we recognize as components of the electric field and magnetic field, but they're all part of the same tensorial object.
And why is it a 0,2 tensor, not like a 1,1 or a 2,0 tensor?
Well, you can certainly create a tensor like that by applying the metric to this first index, but what that's going to do is change some of the signs in here. So the reason it has to be a 0,2 tensor is because, well, I'll show you.
So, to your question first.
Well, I'm not done. Yeah, go ahead.
Okay. This will either be probably simple or complicated. In the Maxwell's equations, they're written on the left. We see kind of anti-symmetry that lends towards the idea of magnetic monopoles. Does that lack of symmetry go away when we write these in 4 dimensions? Okay.
So I think maybe I didn't say anything about this, but these equations are equations of motion. That is, if you write down the electromagnetic Lagrangian and vary it and get the Euler-Lagrange equations from it, you'll get this set of equations. Okay, but that leaves you to wonder where do these come from. The usual case that's made to you is that these equations are true because we can express E and B in terms of potentials. But there's actually a geometric underpinning to that. So this is actually a statement about electromagnetic geometry. or the topology of the electromagnetic geometry. So to actually explain this, we would have to talk about the electromagnetic gauge potential as a U1 bundle over space-time, and then if you make the space-time topologically non-trivial, then that U1 bundle can have a non-trivial, it can have a non-trivial connection over that non-trivial space-time, and so if you want to put in monopoles, this is the set of equations that you actually adjust, because monopoles are actually a change in the topology of the electromagnetic bundle. This is just good old local dynamics. So yeah, I mean, that symmetry was appealing for a very long time. It took people a long time to actually figure out that mathematical reason why these are different. But that's a much longer story for a different day. So it's a feature that pops up in a lot of contexts, though, beyond just electromagnetism. It's not just a happy accident of electromagnetism. So I want to now take these, though, and with those four-dimensional generalizations, rewrite these, because I want to rewrite the equations. And so here we go. This is what's sweet. All of these become d mu f mu nu equals j nu. And d mu f nu lambda equals 0. Okay? The worst looking j I've ever written in my entire life. Okay, so let me explain this for a minute. First of all, we know what d mu is. We talked about that. D mu is just the four-dimensional generalization of a coordinate derivative. And we know that it acts like a dual vector. Okay? F mu nu with two upper indices is exactly what I would get if I raised the two indices here. How many equations does this correspond to? 4, because the mu gets summed over, but there's a free index nu which takes 4 values, 0, 1, 2, 3. 0, 1, 2, 3. So there's 4 equations here, and sure enough, that's these 4 equations right here, the equations of motion. How many equations does this correspond to?
Hopefully 4.
So well, you need to be asking me, what do those brackets mean?
Yes, please.
So the brackets mean you totally anti-symmetrize.
What?
Of course. Derivatizing.
Cool.
So an anti-symmetrization means if I write the expression down and then I write it with 2 of its indices flipped, I put a minus sign on it. Now the problem with that is if the indices are the same, so if so f mu nu itself is an antisymmetric object. Well, I don't anti-symmetrize f mu nu. It's just this expression means to anti-symmetrize it. So here we go. What this means, and you'll probably need this for your homework, is I write it down with a set of choices for these. So maybe I'll choose 1, 2, 3. 1, 2, 3. So that's one part of it. It's one piece of it. This has got 3 indices, so it's got 4 times 4 times 4 possible pieces, right? So there's one of them, but to anti-symmetrize it means that I add to it all permutations of 2 indices with a minus sign. So I would subtract this, because this is related by switching 1 and 2. And then I would subtract switching 1 and 3. Okay? So that's what the anti-symmetrization thing does. But what if this was 1?
You can't.
You can't, right, because when you swap it, that would also be a 1, and that would give you 0. So if you repeat an index under an anti-symmetrization operation, it automatically vanishes. So the only thing that we can do with this expression is pick 3 different distinct values for these 3 indices. But what are our choices? We can pick 0, 1, 2. We can pick 0, 1, 3. We we can pick 1, 2, 3, and we can pick
0, 2, 3.
0, 2, 3, thank you. 4. And so there's 4 equations there. And they, of course, correspond to these 4 equations. But here's the cool thing. These are now 4-dimensional tensor expressions. They're written in terms of tensors. So if I asked you, are these invariant under rotations, what would you say? You'd say yes, because rotations are part of the symmetries of 4-dimensional Minkowski space. But if I also asked you if they're invariant under boosts, what would you say?
Yep.
Yes.
You'd say yes. Okay. But let me ask you something. Boosts tell me how things change when I go from one frame of reference to another inertial frame of reference, right? Everybody on board? These equations are invariant under boosts. But what is a prediction of these equations? What is a certain pretty important thing that comes out of Maxwell's equations if you do the right thing with them?
The speed of light.
They predict the speed of light. But Maxwell's equations are invariant under boosts. So these equations have a built-in speed. You can beat them into a wave equation and they have a speed for the traveling wave. It's c. But these equations are invariant under boosts. These equations are the same if you change to a different reference frame.
So what you're trying to beat out of us is that C is the same in all of the reference frames.
Yes, because these electromagnetic equations are invariant under boosts.
Yeah.
Yes.
Got it.
That's not to say that the speed it predicts the thing will be moving at is some number 3 million meters per second, even though it's already moving at 50 meters per second or something. You know?
It's so all I'm saying is I can work with these equations in one coordinate system and they will predict 3 times 10 to the 8 meters per second. And then I can take them and I can boost the equations and they will predict the exact same number. Which makes no sense by the old Galilean relativity velocity addition formula. If I'm working with some physics and something is moving with a certain speed in a certain reference frame and then I boost to another reference frame, the speed of that object should change. It should be effective. Okay? And the velocities of real physical massive objects, if you boost, those will change. It's c. It is the particular velocity associated with these equations that is invariant under boosts, which we know is one of the tenets of special relativity. Yeah.
So is that the same or different mechanism that tells us that C is our speed limit?
Well, actually, yeah. That's a subject which I thought I might get eclipsed today, but we're not going to. So that's going to take us into relativistic kinematics and dynamics to actually see that it's a speed limit. And it's not. I want to be careful in calling it a speed limit because you can always go faster than the posted speed limit on the highway, but you can also accelerate up to the speed limit. You cannot accelerate to c. C is the point you can always strive for, but you never get there. Conversely, if you are allowed to travel at c, like if you're light, you can only travel at c. You can never slow down. So the idea of talking about it as a speed limit is kind of, it's a limit in a precise mathematical sense, but we have to be a little bit more careful about the analogy with driving and so forth. All right, so next Tuesday, we'll get together and talk about relativistic kinematics and dynamics. I'll add a couple of homework problems and see you next Tuesday. Will somebody?
How?
Yes, sir.